Welcome, everyone. The event is now live. John, please take it away.
Thanks, Annie. Hi, everyone. Welcome to the latest installment of our ongoing editorial webinar series, Coffee Talk. Each hour-long, information-packed episode organized by the hardworking folks at Redmond Magazine features the observations and insights of independent experts on a wide range of tech industry topics. Many thanks to the underwriting sponsor of this episode, high-performance enterprise networking solutions provider Juniper Networks. Without their support, this series would not be possible. And thanks to you for joining us. I'm John K. Waters, Editor-in-Chief in the Converge 360 Group of 1105 Media, and I'll be your moderator. The topic of today's talk is Data Center Fabrics 101, what they are, why you need them, and how to implement them. And our lead presenter is Joey D'Antoni, Principal Consultant at Denny Cherry and Associates. But before we get going, just a bit of housekeeping. This episode is being recorded for later access. Keep an eye out for an email with a link to that recording. It'll be coming your way in the next few days. We'll make some time at the end of each presentation for questions. Please feel free to type your questions into the Q&A box at any time. We'll do our best to get to all of them. Our sponsors provided some extra resources you absolutely will not want to miss. They're available now in your console. And as a small thank you to the first 200 attendees who stick with us to the end, we will be sending you a $5 gift certificate to Starbucks. It's a cup of joe to go with the info. Now I'd like to introduce our first presenter. With more than 2 decades of experience at Fortune 500 companies, Joey D'Antoni has become a well-known thought leader in cross-platform IT. He's both a VMware vExpert and a Microsoft Data Platform MVP. He has worked extensively on database platforms and cloud technologies, and he has a high level of expertise in performance tuning, infrastructure, and data recovery. You guys are in for an awesome session. Take it away, Joey.
Thanks very much, John, and welcome, everyone. One of the things I wanted to get started with before we kind of dive down into data center fabrics, because this is largely a networking topic. So we're going to be focused on kind of core networking technologies and how we build that networking within our data center. But one of the topics I wanted to make sure everybody was on the same page on and understanding was software-defined networking. And I remember, I strongly remember this, so it's kind of funny. The first time I heard about software-defined networking, I was a principal architect, infrastructure architect at Comcast Cable. I'm sorry if you're a customer. It was a good place to work. But anyway, I heard about software-defined networking, and I was like, how do you software-define cables and fiber optic lines between buildings? Well, it turns out if you have enough cable and enough fiber optic lines, you can build a software layer on top of it. And software-defined networking is a really important step. And in those nascent days, I remember hearing about VMware NSX and kind of laughing it off. But now I get frustrated when I have to deal with, kind of traditional network infrastructure at a customer. I was working with a cloud customer the other day, and we kind of completely redid their network strategy in one PowerShell script because everything was software-defined. So software-defined networking represents a big step forward from traditional networking. So it gives us increased control and greater flexibility. Instead of manually programming multiple vendor-specific hardware devices, your developers can control the flow of traffic over a network by simply programming an open standard software-based controller. Network admins also have more flexibility in choosing their network equipment since they're just choosing a single protocol with a number of hardware providers through a single controller. This also gives you customizable network infrastructure. With a software-defined network, administrators can configure network services and allocate virtual resources to change the network infrastructure in real time in one centralized location. So just to give you the example of what I was doing for my customer the other day, I'm working with a customer to do kind of this big automation project in Azure. And one of the requirements that we've come across is that if we're going to use a SQL Server always-on availability group in Azure using their automated template, it has to be split across 2 different subnets. So the change we decided to make was to split their subnets. And for those of you who speak networking, you'll know what I mean. The subnet we had allocated for the database server, we decided to split that. Instead of being a /26, we made it into 2/27s. And instead of having to go to each switch and customize that, I just ran one script to redefine all those subnets as /27. So lots of easier ways to do this. So it can optimize your flow of data. And it also lets you have a more robust security model. SDN allows you to have visibility into the entire network, which provides a more holistic view of security threats. With the proliferation of smart devices or IoT devices, and we know the S in IoT stands for security, that are internet connected, with software-defined networking, it can be a lot easier to segment those things out than in traditional networking. Operators can easily create separate zones that require a different level of security or immediately quarantine compromised devices so they can't infect the rest of the network. But the key difference between SDN and traditional networking is just infrastructure. SDN is all software-based, where traditional networking is hardware-based. And obviously, SDNs do have hardware that run, but they also have kind of a common control plane that's software-based that gives you a flexible, more flexible than traditional networking. So you can easily control the network, change configuration settings, provision resources, and increase network capacity, all from a centralized interface. Typically, that's going to be backed by an API to kind of greatly simplify and reduce the effort. All right, so now we've kind of established a common plane on what SDN is. And if you've ever worked in any cloud networking or any really modern networking, you've probably used SDN. What is a data center fabric? So the term itself can be as meaningless as a network switch or cloud. Almost every networking vendor is going to announcing or selling a data fabric solution, and the vendor products are somewhat similar, but they're a little different. But if you're trying to choose the best solution for your data center, you really want to figure out what's going on behind the scenes in this architecture. And having in-depth understanding of how these fabric architectures work can help you identify their benefits. And the fabric is generally considered to be the layout of how the computing, networking, and software components work together to deliver IT services. It also happens to be the name of Facebook's data center plan for their data center fabric. And Facebook's been not my favorite company in the world, but I will say they've been really open in terms of what they've been doing in terms of hardware, especially on the hardware side. They've contributed a lot to the Open Compute project, which is kind of an open data center project, and they've been doing a lot of data sharing of what they're doing in these large-scale data centers. And one of the things I think that's challenging for folks, especially who work in smaller organizations, to understand is just the level of complexity you start to reach when you start trying to automate things in large-scale data centers. I know before I worked at Comcast, it was hard for me to understand just the scale of solutions in big data centers like that, and the way you have to think about things differently. With the way the fabrics are defined in Facebook's model, it's derived from switching technology. So this is the layout of how connections are made in a matrix of switches and servers. And the term fabric here comes from the crisscross nature of a networking fabric. And as data centers become larger, this crisscross matrix between server planes, switches, edge switches, and server pods grows larger and larger. And these data centers are far more complex than traditional IT networks. And one of the other things that I think is so rapidly changing, and we'll talk more about how AI impacts this later in the talk, is that network architectures are constantly evolving depending on the size of the data center and the types of the applications that people are building. When you're an organization like Facebook or even the cloud providers like Amazon and Azure, they're building new and different applications that have to support different types of interaction. You know, some internet, some private, some highly private. So being able to support all those things means that it's kind of challenging to do that with traditional networking. But with a fabric is that all of the servers and switches are connected to one another and can communicate securely through networking hardware and software. One of the key problems in any data center is just the total number of connections, how traffic is flowing between all of those services, and the most efficient way to connect those different elements. This poses a challenge on both a hardware level as well as the physical cabling and conceptual level. So it's important to know how these data center applications will interact with each other and be exchanged in which patterns. And this image is from Facebook, and you can kind of see here where they have, spline switches that sit on top of server pods. So you can almost think of that like the spline switches or serve the top of rack switches, which are the fabric switches in that diagram. So fairly, oh, sorry. I did not see the slide. There we go. Thanks for that. This is the slide I was talking to there. And you can see these spline planes across servers. Lots and lots of switches to support the infrastructure. Those edge switches are going to provide that big connectivity to your fiber channel outbound and then have scalable uplinks. So we'll kind of talk more about this in detail as we go through these slides. Sorry about that delay on that slide. The principles here of a data center fabric, these architectures are based on behavior between physical devices. So every chassis switch usually has a single active control plane and multiple data planes, making it almost like an in-chassis Kubernetes architecture. Regardless of what's in the chassis, the architecture would be categorized as this kind of architecture when there's a single control plane for multiple physical devices. And that management plane is going to typically interact with your network operator, usually via CLI or a web interface, through an API, network management systems, usually via SNMP, or other external entities, sometimes using NetsConf or other XML or REST-based API. And that management plane software is going to configure the devices and keep track of the current and saved device configuration. Your control plane is going to run those control protocols like LACP, LLDP, CDP, et cetera. And these are going to exchange network topology and reachability information with adjacent devices. And it's going to use the exchanged information or information gleaned from packet sniffing to build forwarding tables, which are then used to forward the frames and packets that are traversing the device. Data forwarding. This plane is going to use the following forwarding tables to forward layer 2 or layer 3 datagrams. The data plane might send packets that it can't process to the control plane. For example, a datagram that's violating an access list, or extract information from forwarding packets and also send that information to the control plane. An example of this would be dynamic MAC address learning. One of the kind of reasons why we're switching to data fabric, and generally speaking, this is one of those technologies, and you've seen this a lot in recent years, and I think Kubernetes is a good example of this, but there are a number of other technologies you've seen that have been driven by things that the hyperscale providers like Amazon, Azure, Google, Facebook, those large-scale companies have learned. And they're cascading down to normal enterprise IT organizations. And one of which is that east-west traffic in data centers has outgrown current generation switching technology. And if you don't know what east-west traffic is, it's traffic that move between kind of edge nodes in a network design. One of the things that's really driven this is the increase in ransomware. Attacks have designed network admins to more securely design their networks in more of a hub and spoke fashion. So we're spreading, we're not just we're only centralizing key things like firewalls and switches, and then we're distributing those data and user workloads kind of into their own either virtual networks or even real physical networks. And the design of that is basically an assumed breach mentality, right? So that if you are attacked, you're limiting the surface area of what the attackers can get through laterally. So those are kind of an important thing. So when a host system in one cabinet needs to interact with another, that traffic typically has to go through that hub. And when we have all this traffic moving east to west in a data center and it's all going through that hub, it can overwhelm that hub. And traditional firewalls are mainly designed for north-south traffic. When we talk about north-south traffic, that's data coming from outside into our data center and data going out from our data center into the internet. But those things fall down when it comes to enforcing east-west traffic policies, especially in a zero-trust manner, because having to make dynamic, this is really something I do almost for a living all the time, is working on these software-defined firewalls that help customers secure their traffic from attackers, but at the same time allow their business traffic to flow. So these are kind of the challenging bits of this. The other aspect that is challenging, and we've talked a little bit about Kubernetes and where it comes into play here, is that traffic from microservices-based applications, so like if you have Kubernetes pods running on a physical host, they may be connecting to other containers on that host, which leads you to a blind spot because that traffic never actually leaves the host, and it could make you vulnerable to threats. And I'm not 100% aware of any attacks that have used this pattern, but it is something you could very much see, especially if you had, say, a Kubernetes deployment where you had a sidecar container and a data container that were perpetrating an attack, knowing that that data would never leave the host, so it would be a little bit easier for it to go undetected. Something to keep in mind there. So when we talk about data center fabric and the architecture, this is a sample architecture, and once again, this is from Facebook, and this is a leaf spine architecture. And there are many terms that are applied to different pieces of data center fabric, like this top of rack switch, which is going to manage other switches in a rack and then connect it to larger devices like these fabric switches, or sometimes they're known as spine switches, which connect out to metro networks or aggregation points. This layout here is known as leaf spine, and this helps. This eliminates a layer of switches in between, which might be more common in like a traditional enterprise network, especially an older one. The common theme here is that as data center traffic gets funneled into the networks, it gradually works its way into larger and larger pieces of equipment into a backbone of sort. Either the company's own large fiber network or that of a service provider. A lot of the traffic in the data center probably doesn't leave the data center at all, and this is that east-west traffic that we mentioned. And this consists of applications and servers talking to one another, either inside the data center or in adjacent data centers, so like inside of an availability zone, rather than that north-south traffic, which is typically going to make its way into a fiber channel, high bandwidth network to go someplace far away or asynchronously. This leaf spine design helps the data center become more modular and accommodate the massive requirements of today's data center. You have to take into account how to handle terabits of data and ever-increasing connectivity needs. So having these bigger switches and distributing that load allows for a more balanced network and allows for better overall performance. And that's really the goal of this architecture and the whole concept of data center fabric, is to better serve the network, allow you to have better performance, and more easily add scale and performance to the network. So I know we've talked a lot about east-west networking, but that really is the driver here. As we have come up with more complex application patterns, so as we've moved from monolithic to disaggregated aggregations and microservices design patterns, traffic patterns in the data center have moved. They shift from north and south between devices within and outside the data center, to between devices within the data center. And as you move beyond these monolithic applications, you'll also typically see an agile IT approach develop, where enterprises will deploy applications more quickly and in smaller steps and respond to transport requirements that can also change rapidly. Just yesterday, kind of that same project I was working on with those SQL servers in Azure, we had a whole bunch of new network requirements thrown at us mid-project. in order to service that, because we're working in a software-defined infrastructure and a cloud provider, we can pretty quickly stand up a couple of things. There's a third party involved, so we have to get them connected into our environment. But beyond that, we can actually set up the core infrastructure. I could have done it while I was on the call yesterday, whereas in a traditional world, we would have had to get network lines run, all sorts of complexities in place. The other aspect here is many organizations are moving to virtualized workloads like containers and software-defined networks to support these rapid shifts in capacity, or moving to the cloud. And traditional hierarchical network data center designs aren't well suited to support these requirements. So this lets them have these fabrics and better respond. So you can support shifts in capacity almost on a per application basis. So some other benefits here that data center fabrics have that make them the premier solution for modern data center networks. The scalability, it adapts to flat topology that allows communication between any two nodes in the data center, avoiding that bottleneck problem at the core switch. Low latency and high bandwidth. So this flat architecture reduces the number of hops a packet's going to take through the network, reducing latency. At the same time, it takes advantage of those high-speed connections coming into the network, as well as multipathing to provide greater bandwidth and throughput to meet the needs of high-performance applications. It's funny, it wasn't that long ago that we only had 1 gig capacity within our networks in our data centers, and now, even 10 gigs is probably not enough. Fabrics also simplify our management experience. By separating that network control plane from the data forwarding plane, we have centralized network management and control. We also get high reliability and fast failure recovery. By having all those redundant paths and fast failure detection mechanisms, the network can quickly recalculate and forward traffic in the event of device failure, which provides higher levels of availability and better supports modern applications that have higher SLAs for those customers. So what are the challenges that organizations face when trying to do these changing models in their network? And this is something that is very challenging, especially if you aren't a big scale, or if you are a big scale and you have a large investment in an existing infrastructure network. So if you think about the overall network and then translating those necessary actions to make that change to individual topology networks. So you need a clear and predictable path to scale your capacity and take advantage of this. So leveraging performance and scalability of a distributed control plane to help build this. Looking at software, the way I like to describe changing a network on the fly while things are running is trying to rebuild an airplane while it's in the air. But you definitely need those same controllers in place, and having multipathing is something that can allow you to kind of start building this up side by side. But you have to plan your whole network as an end-to-end, not oversubscribed environment. So you'll have to allocate the necessary physical resources to support your fabric. Those probably need to be pre-built so you don't have a whole lot of passive infrastructure skeleton components. And then have that scale in place and ready to light up as soon as you get everything connected. Testing, obviously very important. And then from a server rack, or data hall or top of rack switches, those top of rack switches now just connect to different aggregation points with different clusters. For spine and edge devices, you ideally want to have those centrally located so that they can easily be switched on and off. And you also want to ensure that there's a lot of software and automation defined in your plan so you can quickly move away from any failing devices. But changing this architecture, especially in an existing data center, is not something that's trivial. So you want to take advantage of your vendors and get that solution. So Fabric offers a lot of challenges. It's a big philosophical change for network engineers. Like I mentioned, I joked when I learned about software-defined networking that wait, don't we need copper and fiber? However, there are a lot of benefits, like being able to survive multiple simultaneous component failures with no impact. Smaller and simple devices mean easier troubleshooting. Automation allows you to create and improve it all faster than your previous networks. You can almost think of it as Lego-style building blocks. However, trying to get this in place is a challenge. But if you're running a very large data center, the benefits are going to outweigh the cost. The buzzword of 2023 and 2024, AI. So what are the challenges of AI in terms of networking demands? And this is something that's been really interesting to see evolve over the last year or so, just because we're seeing the increased use of AI through large language models. I gave a presentation at a conference in the UK, a full day on AI last month. And in preparing for that, I attended a Microsoft event with Mark Rusinovich, who's their CTO for Azure. And one of the things I really hadn't thought about in terms of artificial intelligence systems is just the network capacity. You hear a lot about GPUs, right? So you see NVIDIA's stock price. You hear a lot about how AI is driving GPU consumption. What you don't realize is how much networking that is. You're sending a lot of data. It's one of the database challenges we have. The vector data is very large. Typically, a lot of organizations can't get the capacity they need in one data center, so they're trying to have low latency across globally distributed DCs, so that means their WANs are even bigger. And there's also increased demands for reduced bottlenecks given the cost of GPU time. We always used to joke that if data was waiting on the network as DBAs, it wasn't our problem. Well, given the cost of GPU time, it is your problem. So the network needs to be able to basically service this. And likewise, because of the time that it takes to train those AI models, reliability starts to become the most important thing in our network. We have to be able to be fault tolerant and survive failure and be highly available. So when we talk about networking for AI, some of the things you'll see, like Microsoft is using technologies like InfiniBand. This is still challenging because InfiniBand is expensive and proprietary. Microsoft is kind of committed to it, but you see a lot of other services build on commodity internet with high bandwidth. The big thing here, though, is you want those GPU clusters to be able to communicate seamlessly and being able to align those nodes and edges, because that's really critical to making those AI networks function. You can't have enough bandwidth, and you can't have low enough latency. So all the network challenges we've had in a traditional world just amped up kind of almost to 11. So data center fabrics are the future of network architecture. We've taken advantage of things we've learned in moving to a software-defined networking model, and we've scaled that into these like leaf node architectures that allow us to better scale, support modern application design, and take better advantage of things like SDN. It can be challenging to implement a data center fabric, especially in a running data center that you're trying to run. But overall, it's going to be beneficial to your network organization. It's reducing the amount of work you're going to have to do to scale your network, reducing overall latency because you're going to have shorter paths for that east to west traffic. And it really helps you support the modern security requirements of networks as well as the scale you need. That combined with the fact that AI is really going to be driving those challenges, and we're definitely looking at fabrics being the way to go forward. With that, John, do we have any questions?
We do indeed. I want to remind everyone that you can type your questions in the Q&A box at any time. We'll do our best to get to all of them. Let's see here. Where'd my Q&A go? There it is. Okay. Let's start with this one from Arnie, who's wondering, it seems expensive to rebuild our network. Are there cost benefits to data center fabric? I know you talked about a little of this, but maybe elaborate more.
Yeah, there are, in that like you're able to automate a lot of things. You're potentially able to reduce the number of devices. Maybe that's kind of an it depends. you're definitely going to see better security within the network, which I know security is one of those things that a lot of companies don't always like to spend money on until they have to. But you're going to get the automation and the productivity gains you're going to get are definitely where the benefits are going to come from, financially anyway.
Okay, here's one from Zick who's wondering, does fabric architecture help make our network more secure?
That's a really good question. It's a complicated answer. I would say inherently, not necessarily, but it does. So that's like always the good kind of question. Fabric architecture helps you better support software-defined networking. It also helps you better support that east-west traffic with monitoring. And by better supporting that east-west traffic, you can better isolate workloads from each other. And one of the things I constantly talk about whenever I'm talking about security and modern threats in ransomware is to separate your network components. We don't want everything talking to everything. If you're like a domain admin and you can from your desktop RDP to a domain controller as you, guess what? So can the bad guys. So Data Center Fabric supports the kind of technology that will better allow us to more separate those networks into component parts that have limited communication between each other, and that's what gives you the security. So that's kind of the key thing to take away.
Okay. We've got a question here from Swear who's wondering, what are some of the trends that have driven increased east-west traffic?
I would say the biggest trend there is kind of the mainframe mostly going away, except for a couple of industries, and us seeing more and more client-server type applications. But it's not just client-server applications. We're seeing more complex application architectures. So you're seeing not just a web server and a database server, but you're seeing application servers, API servers. You have caching layers. So each of those things tend to be ideally isolated in their network, but have to talk to each other over specific ports. So you want to narrow down what's there, what can see what, and that's what's driving a lot of that east-west traffic as opposed to just going up and down, in and out of the data center.
Okay, here's one from Ina. I hope I pronounced that right. Joey, how does fabric architecture apply to cloud users?
So it's kind of an interesting background there with cloud. Fabric is going on in the background because the cloud providers are implementing it. And it tends to be that like your ideal network architecture in the cloud, and there's a lot of it depends here, but is what we call a hub and spoke model, where you kind of have your centralized network components in that hub network, and then you have that network connected to a lot of what we call spoke networks. And that's where, like, for example, your virtual machines or your database workloads or your application workloads are going to live. So effectively, you're riding on the rails of what somebody else did in building a fabric architecture, and you're taking advantage of that fully software-defined layer that the cloud provider has given you without having to think about it so much.
Okay. We've got one here from, again, I hope I pronounced this right, Nagy, who's wondering about implementing firewall security with high east-west traffic. Is that an issue?
So one of the challenges there, and I suspect Arun's going to talk a little bit about this, is traditionally that firewall can increase latency. So we're typically just looking, when we're looking at that east-west traffic, we're not necessarily doing packet inspection. We're, in a lot of cases, only just, for example, allowing traffic to flow on specific ports that we've since allowed. Ideally, we'd inspect that traffic to ensure that it's expected and what we want. But on a lot of devices, that can be challenging. So as we hand off to Arun, I'm sure he can probably better speak to that about how Juniper can help with that.
Awesome. Thank you, Joey. That's all the time we have for this episode of Coffee Talk. Many, many thanks to Joey D'Antoni for an insightful presentation, and a special thanks to Juniper Networks for sponsoring us. We couldn't have done it without them. Keep an eye out for our next episode and for your Starbucks gift card. It should be coming your way in the next few days. Thanks, everyone, and have a great day.